Welcome back. Today we're going to look at section 2.7, which is on related rates. In this section, we're going to be looking at real-life applications to using implicit differentiation to solve problems. So with real-life situations, the related rates that we're going to do typically involve finding a derivative based out of time, okay? When you look at a rate in most applications, you would remember things like miles per hour, feet per second, centimeters per minute, right? So everything that we're doing based on a rate, the derivative is going to be taken with respect to time. So for us to do this in the best way possible, we're going to be using the German Leibniz notation of dy dx, or again, whatever your two variables are that we're taking a derivative of and with respect to. It's a more descriptive way to find the derivative, so that's typically what you're going to see in these problems, okay? So no more y primes because it's just too difficult to keep up with all the variables that we're dealing with. All right, so since we're using time as what we're going to be taking the derivative in respect to, typically t, that variable, is not going to be part of your equation. But we've already talked about, we went through problems where you can always find a derivative with respect to any other variable, whether it's in your problem or not. Okay, so keep those two things in mind as we move forward. So here's an example of that, just real quick on the notes that you've already looked at. But the very first example on your notes is about this formula, r squared equals x squared plus y squared. And in this example, you went through and found dr dt. Okay, well, notice that t is not a variable in here, but you can still find the derivative of this equation with respect to t. That has no bearing on what you're doing. Okay, now the top variable obviously has to be in there because that's what you're going to solve for. But again, most everything we're doing in here is going to be with respect to t because we're doing these related rate problems. Okay. All right, so on the next page was all your formulas. Typically, we ask that you know the ones on the left-hand side, the two-dimensional shapes. You guys should know those. They're typically not given to you. The three-dimensional shapes, typically on a problem, they are given to you. If you're doing WebWorks and it's not given to you, then obviously you can use this formula sheet. But typically, the word problems will have three-dimensional shape formulas for you, but not two. Okay, now down at the bottom, I want to go over a couple things, and I've added a few things for you just so that you have them handy. So the first thing is down here on this first triangle. Okay, you have a right triangle at the bottom, but then you have the triangle up here. That really should be a lowercase a and a lowercase b, because in all triangles, sides are lowercase letters, and then the angles are the capital letters that match with it. So over here would be capital A for this angle A, right? Opposite the side. So I just, make sure that you do this correctly. So that should be a lowercase a and a lowercase b. And, which is more confusing, you have capital A, but this is for the area. Okay, so that's not angle A. This is A for area. And then the way they give you the formula, capital BH, so I just changed that to lowercase so it makes sense. But this is not typical the way we remember the area of a triangle is 1/2 base times height, right? It's the same exact formula. They just wrote 1/2, they put the 2 in the denominator over here. So just kind of keep that in mind. I want you to add also how to find the area of a triangle if you're not given the height. This was from trigonometry. And that formula for the area is 1/2 side A times side B times the sine of angle C. Okay, so that's how you find the area if you don't know the height. All right, so that's a new, well, not new, but don't know it as much as 1/2 base times height, but that is another way to find it. Then I also put on here, because you need to know for your trig stuff, your formulas to how to solve for angles or sides in a right triangle, which are your sine, cosine, and tangent properties. And then oblique triangles, remember for triangles that are not right, like this one, for example, you would have to use either the law of sines or the law of cosines. Okay, so take a minute, write those down, pause the video if you need to, but those are more equations that you should know. And again, these are ones you you most likely should know they would not be given to you. Okay? Only volume and 3D shapes would be given to you. All right. Now, if you've already watched the intro video, which you probably already did, you notice that Dr. Taylor added a couple problems that were not on your notes. So hopefully you just wrote those in or did it on the back or whatever. So he did numbers 1 and 2, and then he talked about the formulas, and then he started over with a new number 1 and 2. So he actually did 6 problems with you finding derivatives instead of the 4 that are on the paper. So I just want to mention that. So that was just a typo on your guided notes, but regardless, you hopefully you wrote those down somewhere on your papers, okay? All right. Then his last problem, he started with what we're getting ready to do, which is, taking the derivative and actually finding the rate of whatever it is that you're asked for. So this still was not a word problem yet, but it was the kind of getting you started on how to do that and reviewing our differentiation when you're doing things implicitly. Okay? All right, so before we move on to number 6, I posted on Canvas extra notes PDF file for you guys to print, and hopefully if you didn't do that, again, I would stop maybe and go do that. But on that document, I started with some important information on related rates and then also the steps that I use. Like I said earlier, every problem that you're doing in a related rate situation is different. Okay, we as instructors cannot, go through every single type of problem that's out there because there are infinitely many of those kind of related rate problems. So we do our best to show you a lot of different examples, but to me, what's more important is if we kind of stay consistent with how we solve them, then you guys can take on any problem whether we've done it or not. Okay, so I have this. You guys should print it out anyway because there's extra problems that we're going to work together. But at the top, just some important information. Okay, so all the rates, which are derivatives that you are going to be working with, that you're given, are going to always be with respect to time. Okay, like I just said, miles per hour, minutes per second. Okay, so always with respect to time. Now, here's the thing about your answers, and especially in WebWorks. If a distance is moving farther away, so if the two things are moving farther away from each other, then the rate is positive because that means it's growing. And then if the distance is moving closer together, your rate is going to end up being negative. Okay, so that's important as you do these problems to kind of remember because they're not going to always give you the sign. You have to figure that out. Okay, now sometimes depending on how a question is asked, you may or may not need the sign. And so I have students that get very frustrated with that because they know that the answer is negative because the objects are moving closer together. But the way that the problem is asked of you, it could be something like, at what rate are the two people moving closer together? So if the question is already saying that they're moving closer together, then the rate that you would answer would just be the positive number. And that is confusing, and I totally understand that. So I will just tell you guys, in WebWorks, if you do the problem and you know it's moving closer together and you typed in a negative number and it says that it's wrong, before you panic, try the positive number because, again, it might be the way that the question asked. Because in the question, if they use the word closer, then that's taking care of the negative sign for you. Okay, so just be careful with that and remember to try both just in case you're not reading the problem quite the way that they wanted you to. Okay. All right, so down underneath that, here are my steps. There are 4 steps, and I try to keep this as simple as I can. We're going to go through every problem this way. We're going to write these 4 steps down all the time, and hopefully the more you do it, the better you're going to get, and this will kind of start becoming a little bit easier for you. Okay, I know that typically none of you guys like word problems, but that's what this is all about. Everything we've been doing up until this point has gotten us to here. So you have to be able to solve these. All right, so the first thing you're going to do in a problem is find the rate that's given to you and write it down. Sometimes there's more than one. Write them down and then use the correct derivative notation. Okay, so we'll do that together. Then step 2 is to decide on the rate that you need. Okay, what's being asked of you to find in the problem? And we're going to write that down using the right notation as well. Then step 3, and this is where the biggest part of this process is, you have to come up with the equation that you're going to use to solve the problem. Okay, so you got to figure that out. And the thing about that equation that you're going to write down, it can only use variables in it that are in the first 2 parts of your first 2 steps. Okay, it can only use numbers that are changing. So anything that stays the same, constant values, you got to substitute those in now. And then always make sure you simplify your equation before moving on to the last step. Okay, so there's a lot going on in step 3, and we will talk about it in each problem. All right, step 4, typically when you're done with step 3, you're in the home stretch, but step 4 is to take the derivative of that equation that you simplified. Make sure you take it with respect to time, and then you solve your problem for the specific moment given. Okay, sometimes you have to do some work to figure out what that specific moment is. Okay, sometimes you'll have to find some other variables involved. Again, we're going to talk about all this as we go through these problems. Okay, those are the 4 steps, and if you consistently do those 4 steps, hopefully you will arrive at the correct answer. Okay, all right, so we're going to start with number 6. Let's read the problem. Suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1.5 meters per second, how fast is the area of the spill increasing when the radius is 19 meters? Okay. All right, and then we give you a few hints and some things, but we're just going to go through and talk about this. But again, when you're asked to find a rate, okay, how fast is the area of the spill increasing? That's a rate, which means you are looking for the derivative. Okay, so these are related rate problems. So every problem, you're looking for some type of derivative. Okay, a rate, remember, derivative is the slope, the rate of change at a specific point in time. So that's exactly what we're doing. All right, so this is just an oil spill in a circular pattern. So and again, most of these, drawing a picture will be helpful. Okay, so what do we know about a circle? Typically, you have a radius. Okay, and that's kind of the only things we know about circles. So let's talk about step number 1. We're going to write down what is given. What derivative is given to us? Okay, derivatives. So the way that you're going to find a derivative is to look for the units of time, that is a length over a time, meters per second. So that's a rate, okay? And what is that the rate of? It says if the radius of the oil spill increases, so it's getting bigger, which means the rate is positive, and I want to label this in derivative notation. So since I'm doing radius, okay, I'm going to use dr dt. So it's always the variable that you're given over time. So this is dr dt, radius over time, okay? So this is the length of the radius, meters, that's how long it is, over time, seconds. So that's given to us, and that was 1.5, right? So that's the given rate. Now, step 2 says, find what are you looking for, okay? What do you need? So I always put what I'm given and what I need. Well, it says, how fast is the area increasing? That's what I need, okay? Well, area of a circle, r squared, right? That's the area formula. So I'm going to use dA dt, and I'm going to use capital A because that's area. So dA dt. That's what I need. So I always put a question mark there. That's going to be my answer. The answer to this question is that question mark. What is dA dt? The rate that the area is changing. The thing is, I have to do it at a specific time, okay? So always somewhere else, not in my 4 steps, but I always write down what is my specific moment, okay? So the specific moment in this problem is when the radius is 19 meters, because dA dt will change at different times. The numbers will be different based on how big the radius is, okay? So our specific moment in this problem is to figure out how fast is the area increasing when the radius is 19. Okay, so when r is 19, that's our specific moment that we're looking for. So I just always like to do that because this way I keep up with it and I know that's what I need when I get to plugging in my numbers, okay? All right, so we wrote down what's given to us. We wrote down what we're needing to find. We've got our picture, we got our formula. So now step 3, okay, remember step 3 is to write down the equation you're going to use. So we are doing the area. So we would write down A equals pi r squared, right? That's the formula for the area. All right, here's the thing with step 3. Remember those 3 parts A, B, and C, if you have those in front of you. This formula can only have variables in it that are in 1 and 2. So I can only have r's and a. So if I look at this formula, I have a, which is fine. Pi is a constant, that's fine, and then r. So I'm ready to go. There's nothing I need to do here but go ahead and move on. It said substitute in any constant values. Well, there are no constant values. The radius is going to continue to grow as the circle gets bigger. So there's nothing constant about this. And then it's simplified as far as I can go. Okay, so I've checked all 3 of those things. So now I can move to step 4, which is to take the derivative of this. So the derivative of a with respect to time is dA dt. Right? 1, the derivative of a is 1 dA dt. Okay. Pi is a constant, so leave it out front. And then the derivative of r squared would be 2r, and then I've got to take the derivative of r with respect to t. Okay. All right, so what am I solving for? I need to find dA dt, so I'm already ready to go. Okay, so dA dt, and I'm going to just clean this up a little bit, is 2 pi r dr dt. Okay, so now I can substitute in. 2 pi is just a constant. What is r? Okay, that's my specific moment. So I'm only solving this problem when the radius is 19. So r is 19. And I was given dr dt, which is 1.5. Okay. So I'm going to multiply 2 times 19. Okay, that's 38 times 1.5. That's 57 pi. And you can multiply out that, that's fine. And that's going to be square meters per second. Now, here's a little thing for you guys, because some of you don't like the units. But think about the units for a radius. You know, that's just a singular, one length. So that's why it was just meters per second. But when you do area, remember area are square units, right? So when I write my answer for any area rate, it's got to be square units, so square meters per second. If you're doing volume, then it would be cubic units, okay? So don't stress about the units, just kind of think about the units of this measure, and that will give you the units of your answer. So this is a perfectly fine answer for WebWorks. It's actually probably the better of the answers, because remember, you don't want to round too much. But you could multiply 57 times pi. I'm just going to put approximately 179.07, because I'm pretty sure if I put that in WebWorks, it's going to say I rounded too much. Okay, this is exact, so that would be better. But you can always do the decimal. Just remember not to round it too much. Okay. All right. So there's our first example for a related rates problem. Okay. So you found the rate that the area was changing when the diameter, or when the radius was 19. All right, let's look at number 7. A fireman is on top of a 75-foot ladder that is leaning against a burning building. if someone has, and should be tied, somebody has tied Sparky, the fire dog, to the bottom of the ladder, and Sparky takes off after Cat at a rate of 6 feet per second, then what is the rate of change of the fireman on top of the ladder when the ladder is 5 feet off the ground? All right, so let's draw a picture of this so we can kind of make sure that we see what's going on. So pictures really do help in these kinds of problems, okay? All right, so here's the building, all right? Here's the ground, and here's the ladder that's leaning up against it. So there's the ladder. Not the best drawer, but there we go. All right, so the fireman is up here, right? There's the fireman. Here's the dog tied to the bottom of the ladder. Okay. So there's Sparky. All right, so let's talk about this picture. The fireman is on top of a 75-foot ladder. This ladder, 75 feet. That is a constant rate, right? Once Sparky heads this way after the cat, okay, he's going that way. This ladder, side of the ladder, because it's tied to him, is going to move this way, and this side of the ladder is going to come down, right? But whatever's happening to the rate, how fast it's coming down, the fact is that this side, 75, will remain 75, okay? These two sides, the length of these two sides will change, right? So and you can pick any letters. Sometimes I'll pick letters that match, but this doesn't really give me anything. So I'm just going to call this bottom piece X because that's the horizontal side, and I'll call this Y. Now some of you can do ABC. Some of you see, triangles with ABC better. Doesn't really matter the letters. You just got to keep up with things, okay? So would we agree that as Sparky goes this way and the ladder moves this way, side X is going to enlarge, get bigger? So this rate will be positive. Side Y, as Sparky's heading over here, the fireman is heading this way. So this rate on this side has to be a negative rate. It's getting smaller, right? Side Y will get smaller. Okay, so think about the picture as we write down this information then. All right, so in step 1, what is given to me? What rate is given? I'll put the word rate there, okay? We want the given rate. All right, well, look for your rate in the problem. Anytime you see a rate out of time, right? Distance over time, that is the rate. So it says, Sparky the fire dog's tied to the bottom of the ladder. Sparky takes off after Cat at a rate of 6 feet per second. So depending on how you labeled it, so my side with Sparky is side X, okay? So I need X's rate. X is Sparky because he's on this side. So that means what I am given is dx dt. That's 6 feet per second. So again, you could have let this side be S for Sparky, and this would be ds dt, okay? So up to you how you want to label your picture. Just keep up with your letters. So again, you can use anything you want. It just has to match up. So for me, this is Sparky over here. Sparky is side X. All right, what are we looking for? What is the rate of change of the fireman on top of the ladder when the ladder is 5 feet off the ground? So we want the rate of this side when he's coming down. So that is the rate of this side. So what we need to find, okay, what we're asked to find is dy dt. That's going to be our answer right there. So again, this could have been S for Sparky, and this could have been side F for the fireman. Okay, if that makes more sense to you, then that's fine. It's just hard for me sometimes when I do triangles, I'm either using X, Y, Z, or I'm using A, B, C, because that's in my head, those are the letters that I relate to the triangles and the sides, but it doesn't really matter, like I said. Okay, all right, so let's talk about our specific moment. Okay, it's always good to know that as we're reading. What is the rate of change of the fireman on top of the ladder when the ladder is 5 feet off the ground? When the ladder is 5 feet off the ground, that would be when y is 5, right? That's a specific moment in time because this thing's moving. It's only going to be 5 feet off the ground for, split seconds. And once Sparky goes, he's going to hit the ground eventually. So we want to know what is the rate specifically when y is 5. Okay? All right, so we might have to do some work here. I believe we do on this one. So let's move on and see what we have. All right, so we need an equation to take the derivative of. Well, this is a right triangle with 3 sides. Okay, so we're going to use the Pythagorean theorem. So in our problem, we have x squared plus y squared equals. Now, typically you would put z squared here. But remember, all the variables here have to be the ones that are changing. If there's a constant variable, we put it in now. So I would not use z squared here, okay? Because that isn't, and again, I can't use it because I can only have the variables listed here. I can only see x and y in this equation. So I would not use z squared. I would use the constant, that is side z, so I would say 75 squared, okay? So there's the difference in that problem. So I have the 2 sides that are changing based on the picture, but that ladder will stay 75 feet, and so that 75 will stay in that problem like that, okay? All right, now do you need to square 75? You can if you want to, but you're going to take the derivative, and so that's going to be 0 no matter what it is, okay? All right, so that's why I don't use z squared, okay? I don't use z squared, number 1, because I can only use variables that are in my steps 1 and 2. And I'm also not going to use z because 75 is constant, and all constant values go in step 3, okay, before you take the derivative. All right, so we did all that, so now we're ready to take the derivative. So this would be 2x dx dt, right? X with respect to time. The derivative of y squared would be 2y, and then we would take the derivative of y with respect to t, and then 75 squared is a constant, so the derivative of that is 0. All right, then solve for the variable, dy dt. So I'm going to move this term over to the right, so 2y dy dt equals negative 2x dx dt. Okay. Divide everything by 2y. So dy dt equals negative 2x dx dt over 2y. So we can cancel the 2's. So we end up with dy dt equals negative x dx dt over y. Right? Okay, so now we got to find our answer. Okay, so now we got to go back to our specific moment. So look at what you need. I need to plug in x, dx dt, and y. Well, I have y. My specific moment is 5. I have dx dt, 6. What don't I have, though, is side x. Okay? So this is where I said in my steps, sometimes you have to do a little work with your specific moment. So I know what y is, but I need to find x when y is 5, right? I need to have that as well, because when y is 5 here, I'm going to do the Pythagorean theorem and I can find x. Okay? So I would do x squared plus 5 squared equals 75 squared. Right? That would tell me what side x is when side y is 5. Do the Pythagorean theorem. So we have x squared equals 75 squared minus 5 squared. I just wait and do this all at the end. Okay? So x is going to be the square root of that. And if you now do that, you'll end up with 5,600. Now remember, WebWorks does not want you to round. So when I do these problems, I leave everything the way it is, and I don't round until the very end, okay? When you put these numbers in your calculator, you cannot round them, okay? You will be off by several decimals, digits, and that's going to throw off your answer. So I cannot stress that enough. Do not round, okay? All right, so dy dt. Now I can do negative x, so negative square root of 5,600 times dx dt, which remember was 6, okay, over y, which is our specific moment. Y was 5. Okay. All right, so now I can put that in my calculator and get the answer, and don't round it too much, okay? So that's going to give you negative 89.7998 feet per second. Now, notice my rate is negative. Why? Because remember, side Y was coming down, right? That's the fireman. And so that should give you a negative rate, and it did. Okay. All right. Let's try number 8. Again, I know I'm spending a little bit of time on these, but you guys got to be able to set these up. All right, a street light is mounted at the top of an 11-foot tall pole. A woman 6 feet tall walks away from the pole with a speed of 8 feet per second along a straight path. How fast is the tip of her shadow moving when she is 50 feet from the base of the pole? Okay, so again, another picture would be helpful. Now, think about what we already did. We did a circle with the area formula. We did a Pythagorean theorem. We had a right triangle. So let's see what we have here, okay? All right, so we have a street light mounted at the top of an 11-foot tall pole. So here's a pole. Here's the light up here. Okay, so I know this is 11 feet. And then here's the ground. Okay. All right, a woman 6 foot tall walks away from the pole. So I'm just going to draw my woman here. And again, why I majored in math, because I can't draw. Okay, so there's the woman. She's 6 feet tall. So this distance is 6. She's 6 feet tall. All right. She walks away from the pole. She is walking this way, right? So the distance is going to be increasing. So that rate should be positive. And her shadow. If this is the light, here's her shadow. Okay, here's her shadow over here. And that's going to be increasing as well, right? So as she moves, the shadow, or top of the shadow is going to be over here. Okay, so I'm going to draw a triangle. Okay, best I can. She should be touching that, but, all right? Okay, so this is not a Pythagorean theorem problem. Since we have different lengths, we're going to be using similar triangles, okay? So do you see that you have a triangle here, the big triangle? So we're going to set up a proportion, and then here's your little triangle, okay? Here's your little triangle. Since she's walking and the shadow's moving, these lengths are not specific heights. These don't change, right? She is always 6 feet tall, and the height of that pole, of that light lamp post, is always 11. But what is changing is this. So would we agree that the distance from her to the pole, now I'm going to use letters that make sense. So we'll do W for the woman. Okay. And then how far is the tip of her shadow from the pole? That would be the whole thing, right? That would be her shadow, the tip of her, notice what it says. How fast is the tip of her shadow moving when she is 50 feet from the base? So we need to know her distance and that, right? Okay, so let's do some setup. So number 1, what given rate? What were we given? Okay, find your rate in the problem. 8 feet per second. What is that? Okay, a woman 6 feet tall walks away from the pole with the speed of 8 feet per second. That's this rate. So that would be dw dt is 8 feet per second. 6 is her height. How fast is the tip of her shadow? So we want ds dt. That's what they asked us for. That's what we need. Okay. All right. Now we need a formula. Okay. So now we got to look at the proportion. This is not a Pythagorean theorem problem because we have only part of this, right? So this is not a triangle, this little square right here. All right, so let's talk about the big triangle to the little triangle, okay? It's very simple to set up proportions when you have two triangles that are related, right? So big triangle is 11 side, and the small triangle isn't this side right here, 6, right? It's the height of the lady, so this is also 6 right here. Make this a triangle. We agree? So we can do big to small. So we'll do 11 over 6 equals. All right, now we need big triangle, small triangle, okay? All right, so on the big triangle, what is this side? Okay, the big triangle would be side S. All right, now this is where you got to be careful. What is the small triangle? We need this piece right here. We need from here to here. What is that? That is not W. So you can't put S over W. W is the non-triangle. So think about this. If the whole thing is S and this piece is W, then this piece, the question mark, has to be S minus W, right? Difference, we would take W away from that. That would give us this piece. So this is S minus W. Okay, that makes sense? So we're doing the little triangle. That's this piece, not that piece. All right, so here's our ratio. Do we have just letters that are up here? All we can use are W's and S's. That's all I have. So now my job is to simplify. I do not want to take the derivative of this. That's quotient rules. I don't want to do that. So remember, you always want to simplify. And this is easy to simplify because it's a ratio. You can cross multiply. So we're going to do 11 times S minus W equals 6 times S. Keep simplifying. So this is 11S minus 11W. Okay. And then I want everything to be positive. So I'm going to move the 6S over here. That'll give me 5S. And I'll move this negative 11W to this side. So 11S minus the 6S over here is 5S. And then I'll move the 11W over there. Okay. Now, that's much easier to take the derivative of. So instead of having to do all this quotient stuff, now I'm going to take the derivative of two linear terms. So what's the derivative of 5S? The derivative is 5. So now we're on step 4. Derivative is 5. And then the derivative of S with respect to t. The derivative of 11W would be 11. And then the derivative of W with respect to t. Okay. And what am I solving for? ds dt. So I'm going to divide both sides by 5. So I have 11 dw dt divided by 5. Now, look at your specific moment. I want to talk about this just for a minute. Our specific moment here, okay, is to find how fast the tip of her shadow is moving when she is 50 feet from the base of the pole. So our specific moment is when W is 50. Okay, that's our specific moment. However, okay, look at the problem. Where am I putting in W? To find ds dt, all I need is dw dt, which I already knew was 8. Why didn't this come into play? Okay. Well, when you think about a rate, as she moves, her shadow is going to stay consistently moving at the same rate. They're not going to change at different times. So it's not going to matter whether she's 50 feet from the pole, 40 feet from the pole, or 100 feet from the pole. The ratio that they're changing will be the same. So all we do need is that rate. Okay, I hope that makes sense. Whereas the ones we did before, Sparky and the firemen were going at different rates. So that did matter to have that specific moment. So sometimes you need it, sometimes you don't. Typically you need it. This is one of the very rare cases where you do not need it. So that's not going to happen very often. So ds dt would be 11 times dw dt was given to us. That was 8 over 5. So we end up with 88 over 5, and you can leave that just like that, feet per second. Or you can tell me the decimal, 17.6, okay? WebWorks will take it either way. Oop. So either one of those would be fine, okay? All right, so I'm going to stop here, and I'll do a second part of the video since we're already over 40 minutes. So you can work on the beginning part of WebWorks, or if you want to complete your notes, go ahead and do that now with the part 2 video.